I started out basically being a programmer for engineering and science applications. I progressed to doing system programming and making systems run, and I learned that I was attracted to and had some contributions to make in bigger and bigger systems. But I've been fortunate that I've been able to work for three major organizations that have fostered the science roles, but also high-performance computing. The first one was NASA, and I ran and helped build a computing facility for them. So the types of work that we did there, and some of the things I remember were, for example, getting the space shuttle back into flight after one of the accidents, helping design improvements for the space shuttle. But also, that was the time where we were learning how to use fluid dynamics to design airplanes. And we were using the computers, and this is actually typical of high-performance computing and supercomputing, where the problems that get done on the supercomputing systems today are the problems that 10 to 15 years from now will become commonplace for wherever they exist. And it doesn't matter if it's in financial systems or in fluid dynamics or in building materials. I'm now at working with the NSF on a project called Blue Waters, which will be the biggest sustained system, and we'll talk about, well, I don't want to do that, so it will be the world's biggest sustained computer. What we mean by that is it will be the computer that does real science applications, not just simple tests, and does it faster than any other computer of its generation. And what that means is people can solve these very, very big problems that they can't solve anyplace else, and they can do it faster than in better time to solution than exists before. We focus on sustained computing, which is unusual. Sustained computing to us means solving a problem in a certain amount of time. And it doesn't matter how fast, theoretically, you can solve things with simple tests like LINPACK. What you really want to do is know how you solve problems for real scientists. So we have taken a collection of real science problems. These are the full codes, all the I/O, all the input-output, all the parameterization. And these problems that we're doing, one example is a chemical problem. It's 40 times bigger than anything that's been done before. And we're taking the system, we're solving that problem in a certain amount of time, and that translates into sustained performance. And it'll be the first system that does this for a wide range of science, because the other thing that we have is some systems can do it for a small number of projects. We have a system that we're building that is very well balanced. What that means is it has lots of memory, it has lots of memory bandwidth, very, very fast CPUs, very, very fast interconnect. So it will have more than 200,000 cores or processors. It will have an interconnect that's 2 orders of magnitude faster than what exists today. It will have close to half of an exabyte, which is 500 petabytes of data associated with it, the largest computer of its time, of its class. And that computer will be used for approximately 5 years to solve problems that can't be solved at all. So it is, again, pushing this ability to solve problems today for the first time that then become commonplace afterwards. So there's 3 ways that supercomputing is used to solve bigger problems. The first way is that the problem just gets bigger. You have more atoms in your simulation, you have more resolution in your climate model, you have more resolution in your model of your aircraft. Another way is that you solve the same problem faster, and that's time to solution. So you can solve more problems in the same amount of time. And that's very important for design cycles. It's very important for things like weather forecasting, which has made amazing strides in the last 30 years since the first supercomputer did the first 2D weather map in terms of solving problems in a 6-hour time period, and now they can do 10-day forecasts rather than just 2-day forecasts. And the third way of using supercomputing is to add more physics and more understanding from the base principles of science. And it's not just physics, it's more biology, it's more chemistry, all into the same problem. So you get much better results, and you're able to understand the problem you're trying to solve, and also maybe predict things in a much more high-resolution way, much more accurately. One of the things supercomputers do, and high-performance computers do, is that they allow the scientists to get the physics right first because they're so fast. And then they can make it efficient so it becomes more everyday or more widespread. one of the challenges is just getting the equations right, and then getting them to run efficiently and at scale, because we all are dealing with this multi-core problem, which means we're all now dealing with scale. Nobody can afford to just run things on one CPU anymore. Once you get the physics right, then the challenge is, how do I know that I have the physics right? And that is the merging of your simulation results with your data collection. And that's one of the reasons why we're saying in many of these codes, they get much more complicated. People spend time in certain areas of a code. So if you think of a full airplane simulation or a full climate simulation, there's typically about 15 or 16 different engineering or science disciplines involved with that one code to do that one simulation. So you have people with different expertise involved in different pieces of this with their different equations, all trying to get the physics better, the resolution better, things like that. And then the last thing you have to do is make sure that the data matches what the physics equations are saying. So that's a large data assembly problem, a large data assembly problem, and an analytics problem to understand what the data is telling you, and then you look at your simulations and say, do I have these the same? The other thing that we're seeing more of is people needing to do more what they call ensembles. Ensembles are the same problem being done by the same code with slightly different parameters to begin with, beginning conditions or starting conditions. And you vary those parameters a little bit, and then what you can do is, if you have enough ensembles, and these ensembles run very long times, many areas of science now are doing this. They run different ensembles, and they get a statistical understanding about how accurate their simulations are. And they can find out other things, like in weather and in climate prediction, where severe weather is, or in car manufacturing or crash test. They can find out kind of the unusual failure points in addition to what normally would happen. So they're looking for the unusual case by having many, many cases by slightly varying these parameter sets. So what inspired me was basically making things better for other people. And I do it through technology and deploying technology that others use to do science and engineering, to do things like better car testing, to do things like keeping people safer, make them travel better, better for the environment, so that we understand what we're doing. And that's really what inspires me. I get excited about being able to do that, and I've been fortunate that by using and supporting the computers and building the computers that we do, Blue Waters is my 20th supercomputer, that I'm able to facilitate the exploration of science, and therefore making this a better place to be.